Section 5.1 talks about approximating areas, so we need to talk about summation notation. We want to get used to this notation right here. A summation notation looks like the sigma. That indicates this is the sum you add. This is where you start, and this is where you terminate. Obviously, for this problem, since you're running to infinity, this is gonna continue forever, and this is called an infinite series, or just we call it series. So this is infinite. This is how it starts. You throw n equal 1 in there, you get a sub 1, add. After 1, you plug in 2, 3, 4, all the way to infinity. But if you stop, if you say, you know what, let's start with n equal 1, so the domain would be the positive integers. Now, they could choose n equals 0 sometimes, it depends. It's up to the author. Majority of what we're going to see n equal 1, that's how we're going to write it. This is where we start. So we throw 1 in, we get a sub 1, plus we throw 2 in, we get a sub 2, 3 in. We'll keep on running until we get to substitute the k in, a sub k. That's when we terminate. So the last term would be a sub k, and the very first term will be simply a sub 1. This is a finite series because you stop here. You stop at k. You're adding k of those. Now the rules work. A sub 1, a sub 2, all the way, b sub 1, b sub 2. Let's say that those are two different sequences with constant c. If you see a c, that's a constant. The following properties hold for all positive integers between 1 and n being the terminating point. If you're adding from 1 to n, so if I'm adding the series I equal 1 to n of a constant, let's say 10. Well, when you let I equal 1, that's a 10. When you let I equal 2, that's a 10. When you let I equal 3, that's a 10. You'll add this 10 n times, so it ends up being 10 times n, and that's what this is saying. If you are taking the series and there's a constant involved, you could drag the constant up front, do the series and multiply this one by that. If you're adding two different sequences and you're taking the series of that, you could take the series of the first, the series of the second, and add the results. Similarly, you could subtract those. Now, this is very important. If I'm taking the series from I equal 1 to 100 of a sub I could say that is a sub 1 plus a sub 2 plus a sub 3 plus the series. If I decided to stop at 3, then the next one will be 4 to 100 of a sub I. That's what this is saying. You could add the first 3 terms, plus you start with 4 and you continue on, something that you need for the next class more than this class really, but it's part of the game. Now, if you decided to add 1 plus 2 plus 3 all the way to n, the sum of those would be whatever this number is multiplied by 1 more divided by 2. That's a formula I provide on your exams. You don't have to memorize that, right? Assuming you start at 1 and terminate at n on each of those. If you decided to add I squared, meaning 1 squared plus 2 squared plus all the way to n squared, that will be n. 1 more than that, 2 times that plus 1 divided by 6. And if you decided to do the cubes, 1 cube plus 2 cubes, that is the square of that n wherever you stop, square of 1 more than that, divided by 4. For example, if I decide to take 1 squared plus 2 squared plus 3 squared, 4 squared, and 5 squared, according to this formula, that will be 5. 1 more than 5 is 6. And 2 times 5 plus 1, 2 times 5, that's 11 divided by 6. Those cancel out. That should be 55. This is 1 plus 4 plus 9 plus 16 plus 25. 16, that's 20, 45, and 10 is 55. So that's how it works. But we need those formulas. So we want to make sure we understand how this works. For the following, let's say I'm starting at 5, not at 10. Well, then the formula doesn't apply. You take 5 plus 6 plus 7 plus 8 plus 9 plus 10. And you just add those. What would that be? 10, 19, 27, 34, 45. I could shift this down and shift this down, but we're not going to get there yet. We're not there yet. For now, let's just get used to this. Suppose that the sum of a sub I from I equal 1 to 100 is 15, and from I to 100 of b sub I is negative 12. If I want to compute this, that will be the series I equal 1 to 100 of a sub I plus the series I equal 1 to 100 of b sub I. Based on what's up there, every time I see this, I replace that by, and every time I see this, I replace that by. So this one by 15, and this one by a negative 12, and that turns out to be a 3. If I'm taking this series, I could say that's the series I equal 1 to 100 of 3a sub I minus the series I equal 1 to 100 of 4b sub I. Based on the rules, I could move the 3 up front, and I could move the 4 up front because that's a constant according to those rules. And now simply replace this by the 15, replace this by the negative 12, whatever the outcome is, I'm done. That's 3 times 15 minus 4 times a negative 12. That's 45 plus 48, if I'm not mistaken. That's 93, I think. You know, there it is. So just getting used to those summations really quick. And this is the key. This is what we need for what's to come in 5.3. If I want to figure out what this is, first I see that's a constant. I could drag that up front, and I could take the series I equal 1 to 20. They use K. They could use any letter they want as long as it satisfies that, you know, you're starting at 1 to 20 of k squared minus 5 the series k equal 1 to 20 of k plus the series k equal 1 to 20 of 1. So based on the rules, here I'm adding the squares. These are the squares. I'm adding to 20. So I'm taking 1 squared plus 2 squared plus 20 squared. So that's going to be 20 times 1 more, 21, times 2 times 20 plus 1. 2 times 20 is 40 plus 1 is 41 divided by 6. Minus 5 times, when I work this out, this is taking this 1 plus 2 all the way to 20. So that's 20 times 1 more, 21 divided by 2. And if I get to the last piece, that's the constant part. That is simply 20 times 1, and that will be this summation. You're going to have to do something like this later on. You're going to have 2 problems to work those out with on the homework. Here I could say divide by 2, that's a 10. Divide by 2, that's a 3. Divide by 2, 3, that's a 1. Divide by 3, that's 7. That's 70 times 41. 2870 minus 5 times 2 divides this 10 times. 50 times 21, that's 105, I believe. Plus, of course, you do all of this in a calculator. That's 100 times plus 20, that's 2890 minus 105, that's a 5, that's an 8, that's a 7. So again, plug all of this in a calculator. If I made a mistake, do not hold me to it. Just, I'm trying to get you the idea on how this looks. That's where we start with. Now we're going to leave this alone and come back to it later. Now we want to try and figure out what the area under this curve is. We have y equal x squared is a function. We're running between 1 and 0 and 2. We want to find the area. So somebody came up with the idea of rectangular approximations, and let me tell you what that means. Somebody came with the idea of, okay, I'm going to use 2 rectangles. They used R sub n, indicating the right endpoint. I'll tell you what that means in a minute. And L sub n using the left end point. Let me tell you what that means. So let's start R sub n. If I'm going to use two subintervals, basically I'm going to take this x-axis and break it into two. Well, that's 1 and 2. Here's 1, here's 2. R means when you look at this interval, you take the right endpoint. If x equal 1, y equal 1. Here, if x equal 2, y equal 4, because y equal x squared. You take the right endpoint to be the height of the rectangle, and you find this area. So you say that is 1 times 1. Plus, when you look at the second interval, this interval, you take the right end to be the height of the rectangle. This is the length. This is the width. So you say that is 1 times 4. The area is 5. Now, if you glance at it closely, you notice that that's not the yellow area. We added a lot. We added all of this region. If I was to go in and say, how about if you R sub 4, meaning take 0 to 2, but now cut it into 4 parts. So if I take 2 divided by 4, that will be a half. I'm going to go to a half, 2 halves, 3 halves, and now when I look at this first piece, I'm going to take the right endpoint to be the area that I want. When I look at this piece here, I'm going to take the right endpoint. Do you see that I eliminate that area that should not have been there? When I get to the third interval, I say this is the third interval. I'm going to take the right endpoint to be the end of that rectangle. I'm going to find this. And the last, again, this is the width now. It's half of what it used to be. I'm going to find this area. By doing so, I've eliminated all of that area that should not have been there in the first place. The new area is better than what I got. And I can figure out what that is. This width now is 1/2. Again, it's just a rectangle. The height, isn't it whatever x is, y is that squared? So the height is 1/2 squared. Plus the second piece, the length is also 1/2. But at 1, I'll get 1 squared. Plus this is also 1/2. And the height will be 3/2 squared. Plus this will be 1/2 as well. And the height will be at 2 squared. If I factor the 1/2 out, I'm looking at 1/2 squared plus 1 squared plus 3/2 squared plus 2 squared. Whatever that is. The point is, my new approximation is better than my previous approximation. Just want to make sure I get it right. Oh, I gotta move it a bit more. There. All right. Now, if I decided to come in and say, well, okay, why don't we cut that in half or double those? Let's go for 8. Well, now I'm taking the length. The length is end minus beginning, which is 2 minus 0, divided by 8. That is 1/4. So now I'm going to go on that interval. I'm going to cut this in half. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, and 8/4. And here I'm going to have, obviously, I'm going to go up to the rectangle. By doing that, I've eliminated this new area, the right endpoint, eliminated this area, eliminated this area, and if I go to the last and again say, look, this is the rectangle I'm going to use, and for the last one, that's the rectangle I'm going to use. then I really eliminated that area out. Again, I'm still off, but I am better off than what I started with. And what's going to change? Now the width is going to be, the first piece is going to have a width of 1/4, and the height is going to be 1/4 squared. The second will have a width of 1/4 again, and the height will be 1/2 squared. And then 1/4, 3/4 squared, 1/4, 1 squared. So 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, and 8/4. That will be the area. If I factor 1/4 out, I'm looking at 1/4 squared plus 2/4 squared plus 3/4 squared plus 4/4 squared, 5/4 squared, 6/4 squared, 7/4 squared, and 8/4, which is 2 squared, and I'm done. And that's 1, 2, 3, 4, 5, 6, 7, 8 rectangles. So the more rectangles I add, the better I am. Now, let's try this with a left-hand approximation. Let's say we want to try L sub 2. Well, first things first, I'm running from 0 to 2. So I'm going to take 2 minus 0 divided by 2. The width of each of those is 1. So when I look at the first interval, I'm going to say that one, I lied. When I look at the first interval, I'm going to use, in the first interval, I'm going to use the left endpoint to be the height. So here it's going to be 0. And when I get to this interval right here, you see this rectangle? I'm going to use the left endpoint to be the height. I'm going to say that's the area. And you could tell here we're doing an underestimate. We left all of this and all of this out. So here we're going to say, well, it is 1 times the first height is 0 squared plus 1 squared. If you think about it, if I was putting this on a number line without looking at the graph at all, if I'm using the left endpoint, I'm going to use this and this. If I was using the right endpoint, I would use the 1 and the 2. And here I'm saying this area is roughly 1. What happened if I double those? What happened if I wanted for 4 of those? Well, then I'm going to take the length, end minus beginning, 2 minus 0 divided by 4. That's 1/2. That means I'm going to take this and break it into 1/2, 2 halves, 3 halves, and 4 halves. And now the width is 1/2. Instead of me saying, oh, 1/2 times the height, 1/2 times the height, just put 1/2 out. The first, I'm going to take the 0 still. Now on the second, I'm going to take the left endpoint to be the height. That is 1/2 squared. On the third, this interval, I'm going to take the left to be, and on the last interval, I'm going to go run the left point all the way up to the curve. Well, this is a better approximation, right? But I still have this off, this off, this off, this off. I added a lot. I added this piece, and I added this piece that wasn't there. Well, what happened if I really go for 8? Then the length is going to be 2 minus 0 divided by 8. That's going to be 1/4. So I'm going to break this into 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4. The width now is 1/4, and I'm going to have 8 of those, so I need more space. Let me move that a bit down. Here we go. So when I get to the first interval in this case, I'm going to take the left endpoint. In this case, it's a 0. When I get to the next, I'm going to take the left endpoint, so I added this area. That's pretty good. 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, and 8/4. So basically each interval I go on the left, each interval I go up to the curve, I'm adding this piece now. Each interval, I go on the left. And you can tell what's going to happen as n increases my approximation. Here I'm leaving some areas out. Here I'm adding some area that shouldn't be in there, which means that's an overestimate. Here I'm having less than what I should. So now let's put all of that in perspective. If I wanted to find L sub n, basically delta x, which is the width, will be the end minus beginning divided by n, whatever n is. If you want 2, then each of those is 1. If you want 4 intervals, you're going to have a half, and so on and so forth. So now let me do this without the graph. If I was thinking, look at this. If I was to put the number there, and let's say I want to find L sub 4 and R sub 4, but without the graph. L sub 4, delta x, so I'm going to take this x-axis, and I'm going to take 2 minus 0 divided by 4, that's a half. I'm going to start at 0, I'm going to move 1 half, 2 halves, 3 halves, 4 halves, 4 intervals. If I decided to go by left, and again, f of x is still x squared. If I decided to go by left, I'm going to look at the first interval, which is 1 half, and I'm going to take the left endpoint, which is f of 0, plus on the second interval, I'm going to take f of 1 half. On the third interval, I'm going to take f of 1, and on the last interval, I'm going to take f of 3 halves, and that should make sense. That is, I take the left endpoint, the left endpoint, the left endpoint, and the left endpoint. If I'm doing the right-hand approximation, when I look at the first, it's still 1 half. And on the first, instead of taking the 0, I take the right f of 1 half. On the second interval, I take f of 1. On the third interval, I take f of 3 halves. And on the last interval, I take f of 2. So the left hand takes 1, 2, 3, 4. The right hand takes 1, 2, 3, and 4. Now, in this case, f of x happened to be x squared. I could say 0 squared, 1 half squared, 1 squared, and 3 half squared. But if it's anything else, I could just use that. So in general, when I'm looking at an interval, I take delta x to be, so say going from A to B, I take delta x to be end minus beginning divided by n. If I wanted to do R sub n, the right-hand approximation, that would be, again, let me put that on a number line for you really quick. If I put this on a number line, so I'm starting at x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, dot, 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 x sub I minus 1, x sub I, dot, 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 all the way to x sub n. This is the end, this is the beginning. If I'm doing right-hand approximation, wouldn't that be delta x times the right hand, this height? So that will be delta x, but they're going to all be delta x. All of these are equal. I just factor that out. It's going to be f of x sub 1, whatever f of x is. If it's x squared, then it's x squared. Plus, on the second interval, don't you take this height, f of x sub 2, f of x sub 3, dot, 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 f of x sub I, plus f of x sub n. And wouldn't you say the right-hand approximation is delta x times the series I equal 1 to n, f of x sub I? And what is that? That's approximately the area under the curve. The bigger n is, the better my approximation is, as we discussed. Here it's going to look like a bunch of those. Here it's slightly overestimate, but as I fit more and more, that becomes more and more accurate. Now here's an example. Now, you don't need to graph it. Let L sub n denote the left endpoint and R sub n denote the right endpoint. Okay, in the following exercise, compute the indicated left and right sum for the given functions. Okay, they want both. They want, in this case, R sub 4. And in the next problem, they ask for L sub 6 right there. So, for this one, delta x is the first thing that I look at. That is end minus beginning, divided by how many intervals they want. So that's 1/2. I'm going to take this and put the number. Again, I don't need the graph. I'm running from 0 to 2. 0, 1/2, 1, 3/2, 2. So I'm splitting that to 4 equal parts. If I'm using the right-hand approximation, I'm going to say this width is 1/2, this width is 1/2, this width is 1/2, and this width is 1/2. So that's 1/2 times f of, and let's see how that works. If I'm doing the right-hand approximation, on the first interval, I'm going to take the right endpoint, then the right, then the right, then the right. There should be 4 of them. F of 1/2 plus f of 1 plus f of 3/2 plus f of 2. And now all what I have to do is get my calculator out and figure out what's 1/2, what's 1, what's 3/2, what's 2, add them up, and that will be my answer. And let's see what we're going to do. So we're going to use the answer, but it's not going to be that simple. We have to approximate that 4 times. So if I take 0.5 is the first, 0.5 enter, I'll take my answer squared minus 2 times the answer plus 1. So f of 1/2 is 1/4. That's very good. You could write it in decimal, you could write it in fraction, it doesn't matter. I'd probably say fraction is quicker. That's 1/4 plus f of 1, 1 plus 1, that's 2 minus 2, that's 0. You could use the calculator if you like. Take 1, enter, go back. Oh, I forgot that this. Oh, come on. There it is. And there's the 0. 3/2, enter. If you put 3/2 and you evaluate, 3 divided by 2, enter. Now if you go back, no, not that, up. There we go. It's 1/4 again. And if I put 2 in there, okay, forgive me, that's the wrong sheet. If I put 2 in there, 2 enter, recall the last function, it's telling me it's a 1. Now I could show you how those work without a calculator, but you have a calculator. If you put in 2 in there, you get 4 minus 4 plus 1, which is 1. So this will be 1/2 times 1 plus, again, you could do all of this on a calculator. Take 1 divided by 2, parentheses, 1/4 plus 1/4 plus 1, whatever that is. If your calculator gives you decimal, write it in decimal. If your calculator gives you fraction, give it in fraction. It's 3/4 or 0.75. It doesn't really matter, right? This is 1 plus 1/2. This is 3/2, which is 3/4. But no need to do that by hand. And what's going to change on this problem? This problem, we're running from -2 to +2, not from 0 to 2. We're running from, there's -2, there's -1, there's 0, there's 1, there's 2. So my delta x will be end minus beginning divided by, in this case we want 4. That is 1. They want to go by 1 unit, so pretty much what I labeled. And what are we going to do? We're going to take the right hand. When we look at the first interval, we're going to take delta x. So r sub 4 is going to equal delta x times f of -1 plus, on the second interval, f of 0, or simply look at the numbers, take the right endpoint, right endpoint, right endpoint, and right endpoint. Again, you could plug those in by hand if you wish. You could use a calculator, whatever makes you happy. So f of -1/2, that's 1/2. F of 0 is 1. F of 1, 1/2, and f of 2, 2 plus 1, that's 1/5. On a test, I have no problem you leaving the answer like that. For the homework, you're going to either plug it in a calculator. So take 1/2 plus 1 plus 1/2, or are you going to do it by hand? One of the two. Plus 1/5. And the answer, decimal 11/5 is fine. Or you could simply say it is, what is that, 2.2? It doesn't really matter. And that's pretty much how this game is going to be played. Now I'm going to get to the next. This one we're running from 2 to 5. So let's say this is 2, 3, 4, 5. We're stopping here. We went, oops, wrong color. We went L sub 6. We want 6 subintervals. So delta x is going to be end minus beginning over 6. That's 3 over 6. That's a half. So we're going to go half of each of those. If I start at 2, this is 2 and a half, 3, 3 and a half, 4, 4 and a half. These are the intervals. Now, when I look at the first interval, I'm going to take the left endpoint of each of those. So on the last interval, I'm going to take the left endpoint. It turns out to be delta x times f of 2 plus f of 5 halves, or 2.5, f of 3, f of 3.5, f of 4, and f of 4.5 will be the last. On the last interval, I'm going to take the left endpoint, which is 4.5. 1, 2, 3, 4, 5, 6. How are you going to approximate that? Well, it's up to you. That's 1/2 times, and you want to use it by hand, you can. You want to use a calculator, you can. If I take my calculator and say, now let's take 2 is the first interval. Here we go. Now it's third. If we take 1 divided by parentheses, we want the answer times the answer minus 1. So when you plug 2 in, you get a half. Plus, when we plug in 2.5, we get 4/15. If you're going to copy decimals, then you need to really carry on 5 or 6 decimals. If we take 3, recall the function again, that is 1/6. If we get 3.5, recall the function, we're talking about 4 over 35. And if we get a 4, (112), and if we get 4.5, we get 4 over 63. Now, if I want to match the answer in the back of the book, 1, 2, 3, 4, 5, 6 of them, it's easier, much easier for me to say, well, look, oh man, I did it again, I'm sorry. If I take 1/2, 1 shot, times 1/2 plus 4 divided by 15, make sure you're plugging things properly, plus 1 divided by 6, plus 4 divided by 35, plus 1 divided by 12, plus 4 divided by, assuming I made no mistakes, the answer is 43 over 72. Normally the answer in the back of the book is in terms of decimals, and in terms of decimals, that is 0.5972, 0.59722222. That's my approximation of the area using 6 subintervals. Now, we want to make a general case. So suppose we have y equal f of x, and oh, that's y, that's okay. Suppose you want to find the area under the curve y equal f of x. Suppose we're starting from a to b, and there's the area that we want. So what we're going to do, we're going to call this x sub 0, and we're going to call this x sub n. What I'm going to do, I'm going to break this into n subintervals. So I'm starting with x sub 1, x sub 2, x sub 3. There's the ith interval. So, you know, if this is I minus 1. And if this is x sub n, this is the one before that. And what we're going to say, look, this area right here is going to be roughly the area of the yellow part, of course. That's roughly, I'm going to use r sub n. That's the series I equal 1. That's going to equal delta x times f of x sub 1. And we're talking about this rectangle right there, plus delta x times f of x sub 2. That would be this second piece. This third piece will be delta x times f of x sub 3. Now the list goes on, plus delta x times f of x sub I minus 1, plus delta x times f of x sub I. And if I'm using the right-hand approximation, the last piece will be delta x times f of x sub n. So if I really look at this, I could say this is roughly, so this is the series I equal 1 to n. They all have delta x in them. I could factor that out. And I'm looking at f of x sub 1, f of x sub 2, 3, 4, 5, f of x sub I. And that would be roughly what the area equals. So in general, we want to transfer this to what's known as a Riemann sum. That's really in the next section, the core of using this, but they introduce it in this section. Let's talk about that. This sum looks very much like this sum. Delta x is simply the length of the interval, the end minus the beginning, divided by n, depending whether you want 4 subintervals, 6 subintervals, 8 subintervals. You take the length of the interval. On the previous problems, we started from 0 to 2. So the length was on 14, it was 2 to 5. The length was 3. And we divide that by whatever n is. And this summation, we're going to set it based on the right-hand approximation only. Now, the only difference between what they have and what we have is this x sub I star. Our x sub I is I times delta x, provided you start at 0. And if you don't start at 0, then you have to shift that a bit and say, look, if a is the starting point, it's a plus I times delta x. Let me elaborate on that really quick. So here, when we want to start, let me start with 0 first. That one. When we want to find 4 subintervals, if you're doing, again, only the right, we just want the right. When we want to find the first x value, didn't we take the starting point was 0 and we added delta x to it? We added 1/2, and that gave us x sub 1. When we wanted to find x sub 2, didn't we take the start plus, and don't you add another delta x? So that's 2 times delta x. Yeah, which is the one in this case. When we wanted to find x sub 3, didn't we say that's 0 plus, add another delta x, right? So 1/2 plus 1/2 plus 1/2, that's what the 3/2 is. That's 3 times delta x. So do you notice this is the starting point, which is 0 in this case, plus here 1 times delta x, here it's 2 times delta x, and here it's 3 times delta x. In general, it's a plus I times delta x, because whatever this index is, that number is. Let me elaborate on the next problem. We did another one here. We started with, again, when we wanted to find the first x, well, didn't we say the first x is -1? Do you notice they're labeled? Isn't that -2 plus delta x? What's delta x in this problem? It's 1. So didn't we add 1 to this to get that? Which is delta x. When we wanted to find the second 0, didn't we say x sub 2, which is that f of that x? Isn't that -2 plus? Don't you add another delta x? Didn't you add another one, and that's how you get the 0? We started at -2 and we added 2 times delta x to get the 1, the third. x sub 3. Didn't we take the starting plus 3 times delta x? And when we wanted the last one, didn't we take negative 2 plus 4 times delta x? In general, wouldn't you say x sub I is a plus I times delta x? Because if this is 1, that's 1. If this is 2, that's 2, 3. And that's how it works. Assuming you take the starting point, that's how you find all of these points. So that's what we're talking about here. X sub I is a plus I delta x. If you start at 0, that's 0. If not, then there it is. Now, the only difference between our sum and Riemann's sum, Riemann, his x sub I star is in the ith. So he went to this right here and he said, in general, let's say I pick x sub I star in there. The difference between ours and his, so it's still a plus I times delta x, but his x sub I star doesn't have to be a right, a left. It has to be just in there somewhere. That's the only condition. Now, I'll talk more about, well, in the next set, and again, we're not going to use this in this section. This is really mainly used in the next section. That's the core of where we're going with this. Let f be continuous. The only condition for this to work, let f of x be continuous. If f of x is positive, it's non-negative, and this summation is defined by the Riemann sum, where pretty much that's x sub I star and there's delta x. Then the area under the curve will be the limit as n approaches infinity of this sum we just found. Now, why doesn't it matter where this is? Because if you're taking an infinite amount of those as n approaches infinity, if you're fitting an infinite amount of rectangles under that, then they're going to be infinitely close, and it doesn't matter whether you choose a right end, a left end, or a midpoint, or anywhere in there. Since those are so close, you're going to get the area. And notice it's not an approximation. This was an approximation. By taking the limit as n approaches infinity, like section 4.6, then we could figure out exactly what the exact area is. And now we're going to practice a bit more on this left hand, right hand, and go from there. Okay, well, it says compute the left and right Riemann sums L sub 4, R sub 4 respectively for 2 minus, let me see. Okay, I can shift this just a bit to the left. Oh boy. Come on, where are you? Okay, if I was to set this right there. All right. So, L sub 4. I'm looking at the interval from -2 all the way to 2. And we want L sub 4. L sub 4, we take delta x, that is b minus a minus a -2, so plus 2 divided by 4 intervals. So each one of those has a length of 1, 1, 2, so here we go, -1, 0, 1, and 2. If I am using the left-hand approximation, when I look at the first interval, I'm going to take, so 1 times f of -2. When I look at the second interval, I take the left endpoint. When I look at the third interval, I take f of 0. And when I look at the last interval, I take f of 1. So that would be the actual left-hand approximation. And in this case, I really don't need a calculator because f of x is 2 minus natural log of x, absolute value of x. So f of -2, that will give me a 0. F of -1, 2 minus 1 is 1. 2 and a 1, that's pretty much 4. If I do the right-hand approximation, R sub 4, what will change? The width will still be the same of each of those. It's right there. Now, when I look at the first interval, I take the right endpoint, so f of -1. When I look at the second interval, I take the right endpoint, f of 0, f of 1, and f of 2. and we know what that is. We worked out this one, and this one. So we know that is 1 plus 2 plus 1. And what's f of 2? If I put a 2 in there, I'll get a 0. In this case, they happen to match. That's the first part. Then they say compute their average and compare it to the area under the curve. Well, the average is 4. Now, what's the area under the curve? If I draw this 2, negative 2 to 2, it's an upside down, and I'm only interested in that area from negative 2 to 2. Well, that's a triangle. The area of that is 1/2 base from negative 2 to 2. The base is 4 units, and the height, we know that's 2 units. So that is, in this case, it happened to match because it's a straight line approximation. I'm talking about this because these are straight lines. You're getting the same. That's just a coincidence. It doesn't always happen. And how about this problem? Well, the same deal. If I look at this, they're breaking this again from negative 2 to 2. That's not bad. So and they're doing 4 subintervals as well. So we're going to do that again. When I say let's find L sub 4, that's going to be 1 times left hand, it's going to be f of 0, f of negative 2, plus f of negative 1, plus f of 0, plus f of 1 on the last interval. And when I do r sub 4, that's going to be 1 times f of negative 1, the right endpoint of each of those, plus f of 0, plus f of 1, plus f of 2. And in this case, if I take negative 2, plug it in, that is a 0 plus square root of 3 plus 2 plus square root of 3, and that turns out to be 2 plus 2 radical 3. The left hand endpoint f of negative 1 is radical 3 plus 2 plus radical 3, and I got those 3 from right there. The last one, if you put a 2 in there, you get a 0. So those are matching again. That is not the norm, but it's okay. They say compare that with the actual area. Well, let's find the actual area. So if I look for the actual area, that's x squared plus y squared equal 4 is a circle with a radius of 2. If you solve for y, y squared equal 4 minus x squared, that's still that graph. And if you take square root of both sides, it should be y equal plus or minus the square root of 4 minus x squared. Y equal positive the square root will give me the upper half of that, and y equal negative the square root will give me the bottom half of that circle. So this graph right here is the upper half, since that's a positive, of a circle with a radius of 2. And if I find the area of that, now you might be asking, why are we doing this work if we could find the area? Because they're giving us very special functions. Pretty soon that's not going to be possible. Area is going to equal 1/2 of the area of a circle, which is pi times r squared. That's going to be 1/2 pi, and the radius is 2. So that's going to be 2 pi. So the exact area is 6.28, 2 times 3.14. And if I take 2 plus 2 radical 3, we're getting 5.46. So you could see we're slightly off, but that's a good approximation. That's, with 4 subintervals, that's pretty good. Now express the following endpoint sum in sigma notation, but do not evaluate. So they want us to write this as a summation. Let's see, we're running 0 to pi, so let's say zero to pi. we want r sub 20. Well, delta x is going to be end minus beginning divided by 20. That's pi over 20. So we're going to start to break this into 20 equal parts, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And this very first piece will be pi over 20, 2 pi over 20, which is pi over 10, 3 pi over 20, all the way. This will be 19 pi over 20, and this will be 20 pi over 20. Well, they're saying set it up, do not work it out. What I need delta x. Delta x is pi over 20. That we got. And x sub I will be the starting point, which is 0 plus I times delta x. So it's I times pi over 20, and we could check again. This is x1, x2, x3, x4, x5. Let's say we want to find x sub 6. 3 pi, 4 pi over 20, 5 pi over 20. It should be 6 pi over 20. Well, if you put x sub 6, that's 6 times pi over 20, and that's 6 pi over 20. So there we go. It does work, of course. So this is going to be, r sub 20 is going to be the sum I equal 1 to 20 of f of x sub I star delta x. Well, r sub 20 is going to be the series I equal 1 to 20. X sub I, we said was, so this is f of 6 pi over 20 times, 6, this is here, f of 6 pi I over 20. And delta x is right there. So what is f of x sub I? Okay, why is that so compacted here? Let me redo this really quick. That's r sub 20 is going to be the series I equal 1 to 20 f of x sub I delta x. There. So that's going to equal series I equal 1 to 20 f of pi over 20I times, yeah, it's right there, I was putting the 6, times delta x, pi over 20. That will be the series I equal 1 to 20. F of x sub I is pretty much putting that in there. That's the sine of pi over 20I times pi over 20, which means I equal 1, I equal 1. You start with this piece, then I equal 2, I equal 3, and you evaluate all of that. That's all they want. Now they give us a graph. They want us to use L sub 8. So we're running from 0 to 8, delta x. Again, this author of this book is very nice. They're making all of these nice integers. That's not normally the case, but whatever works, we'll take it. If we want to use the left-hand approximation to approximate this, so when we look at the first interval, we take the left endpoint, and then the second interval, we take the left endpoint, the third, the left endpoint, and the fourth, we take the left endpoint. So we're using 0, 1, 2, 3, 4, 5, 6, and 7. And again, we go to the curve. And when we go here, oh, I went the other way. That last one was incorrect. We take, when we look at this one, we take the left endpoint. So now we're overestimating. And then the left endpoint. And the left endpoint. And the left endpoint. So we would say this is going to be delta x, which is 1 times f of 0, 1, 2, 3, 4, 5, 6, and 7. We don't get to 8. So that will be f of 0. F of 0 happened to be a 1. F of 1 happened to be a 2. F of 2 happened to be a 3. F of 3 happened to be a 4. F of 4 happened to be a 5. F of 5 is a 4, 3, 2, and 1. Whatever that is. So that will be 4, 7, 10. And 10, that's 20, plus 5, that's 25. I didn't make a mistake. And we have another one, the same deal. We want to run from 0 to 8. We're using left and both. Yeah, left and both. They just want left. Okay, not a problem. If you want to find L sub 8, again, that's 1 times f of, and here it goes. It runs from 0 to 8 again. We're going to do the same thing. F of 0, f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, and f of 7. And that's going to be f of, so the left endpoint on the first, that's 0. Okay, how did that start come to exist? Oops. There you go. And when we go on 1, we use the left endpoint. F of 2, f of 3, f of 4. Of course, we don't need the diagram for that, but I'm showing you what we're doing. F of 5, f of 6, and f of 7. So as we see, we know this seems to be an underestimate. F of 0 is 0. Again, I'm looking at the y's. F of 1 is 1. F of 2 is 2. F of 3 is 1 again. F of 4 is 3. F of 5 is 2. F of 6 is 4. F of 7 is 5. And that's it. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 5, 9, 10, 13, 15, 17, 18. And that's pretty much it for this section. That's how this works. There's our homework.